All right, it is a pleasure to be at UAI. This work is primarily by the first two authors who unfortunately couldn't make it today. And they are Jialin Song, who is my PhD student at Caltech, and Ravi Lanka, who is a researcher at JPL. And I guess we've already seen this set up a few times, but maybe just one more time, because I want to talk about it a little bit more broadly than just reinforcement learning, and that's policy learning. So in policy learning, which includes both reinforcement learning and imitation learning, we have the environment or a world and an agent. The environment provides state or contextual information, denoted S sub t, to the agent. The agent, given this information, makes a choice. Good, it's not cut off. An action, denoted H sub t. This perhaps may influence the state of the next world. And this process continues until some time horizon is exhausted. And the goal is to find some notion of an optimal policy. In reinforcement learning, this goal is expressed as a reward function that is part of the environment that you sample as well as the state. In imitation learning, you often have access to a demonstrator or demonstrations, and optimality is measured by some sort of loss function with respect to imitating the expert behavior. But in both cases, the general paradigm looks as follows. Now, policy learning is hard. One of the big challenges, one of many, is the fact that there are long time horizons. There could also be large state spaces. And learning is challenging because of sparse or expensive feedback. So in the case of reinforcement learning, if the feedback is very sparse, then you can show, in the worst case, that learning can be exponentially hard, exponential with respect to the length of the time horizon. And there are other reasons why this might be hard as well. And this is due to the so-called exploration-exploitation dilemma, where exploration can be very challenging. In imitation learning, where you have access to a demonstrator that is providing you feedback or demonstrations of the optimal actions, it can be infeasible in practice to obtain sufficient demonstrations because such demonstrations may be expensive to elicit. And so in both cases, we would like to somehow make better use of our data, make better use of what's available to us in order to learn faster or more sample efficiently. And so one of the challenges that my lab has been focused on over the last few years is learning to search in combinatorial optimization problems from a policy learning perspective. So here's a very simple example of an integer program. And one thing you can do is you can compile it into a tree search problem, in this case, branch and bound. And you can think of navigating this tree search problem as an agent navigating an environment to reach a high reward state. So the nodes in this tree search are partial solutions of the integer program, which you can think of as a state. The edges are actions or variable selections or variable branchings, which you can think of as actions that this agent can take. And one just simply traverses this state space until one finds a feasible solution, which is a high reward state. And in the general case, you get 0 reward everywhere except for a feasible solution that's of sufficiently high quality. And so as you can imagine, this is a very challenging problem. The size of the state space actually is exponentially large in most cases. And the goal is to somehow view this as an agent and learn to navigate this space efficiently. Okay, so this problem is hard, so what can we do? Well, one thing that we noticed after working on this problem for a while, which motivates this work, is the fact that many of these optimization problems have multiple views. So let's take a simple example, which is a very common one, which is minimum vertex cover. In minimum vertex cover, you're given a graph, and the goal is to find a minimal set of vertices. I hope I'm getting that right. I'm a little jet lagged. That covers all the edges, which has a few vertices as possible. And there are two views. There's a graph view, and people have studied the graph view. And then one can also compile this problem into an integer program, and then subsequently compile that to a tree search problem and solve the branch and bound problem, which is the branch and bound view. And people have studied this view, including my lab. Here's another example where if you want to do some sort of robust or risk-aware path planning and you want to model obstacles in an obstacle course, there are different ways of modeling these obstacles. This is something that's very common in planning and control. You can model them as an integer program, in which case the obstacles are surrounded by a convex polygon, or you can model these obstacles using a QCQP, a quadratically constrained quadratic program, in which case the obstacles are modeled using ellipsoids. Again, these are two different views that essentially solve the exact same problem. Okay, and so I'm going to give you a very short detour of the history of co-training. For those who have joined the community relatively recently, you may not be familiar with co-training. Co-training was a seminal paper published by Avram Blum and Tom Mitchell in 1998 at COLT, the Conference on Learning Theory. And it's inspired by this idea that many problems have different sources of information. And in their case, they were looking at classification. So the one example is classification of academic web pages. And one can use two views. This was taken from Avram Blum's slides from a long time ago. And the views can be the words on the web page or the hypertext link, so the hyperlinked text on the web page. And these can be thought of as two different views, and even if you only have a few labeled examples and a large set of unlabeled examples, you can use these two different views to train two different classifiers that can then subsequently teach each other. And that's the basic idea behind co-training. And this idea was very influential. It was published 21 years ago. It's a long time ago. And in 2008, I won the Test of Time Award at ICML. And in the years since, the many papers have been published that extends co-training, either the analysis or the applications. Many of the applications were in the natural language processing domain. And one question that we thought of from this motivating application of ours was, okay, how do we extend co-training to the policy learning or sequential decision-making domain, which is the topic of this paper. And so what's different about co-training for policy learning? Well, for one, we're making sequential decisions rather than one-shot decisions, so that's different. In our case, we actually have sparse environmental feedback. The original co-training paper assumed that we don't have any more labels afterwards. We just have an initial small set of labeled examples, but for us, we can continue to query the environment. It's just that the feedback is very sparse. Sometimes we have different action spaces. So for example, in the graph view, the action space is actually completely different than the action space in the branch and bound view. So they're actually incompatible in terms of the intermediate rollout stages. Now, of course, these two issues are not always applicable for all problems, but in our general case, we considered all of these issues. Okay, so here's the intuition of how a good algorithm might behave in this setting. So we have a minimum vertex cover instance. We have two different views. We run two different policies on these two different views, and there are existing papers that already study these separate views. We get a solution from these two policies, and then we can, at this point, we can directly compare the two solutions at the terminal states because they're directly comparable, and we notice that the bottom solution is better. And so, similar to co-training, the bottom solutions somehow provide feedback or demonstrations to the top policy so that the top policy can improve based on this feedback. And that's the basic idea. And so one way to start formalizing this idea is to say, okay, we have a distribution of all possible minimum vertex cover problems, or any problems that you want to solve. And I'll call that omega. And we're going to split those into, partition that space of problems into those where the first representation is easier and those where the second representation is easier. And the goal is to let the policy 1 provide demonstrations under omega 1, and policy 2 provide demonstrations under omega 2, and somehow lead to a good and practical algorithm. And so this leads us to study how we can extend existing theory to build a theory of co-training for policy learning. And so let's say we have two MDPs, Markov decision processes. I'll call them M1 and M2. And let's say that there is a transfer function that can translate entire trajectories from one view to another view. A trajectory is just a rollout, so a full solution path in one view. So this is, in practice, often the case. You could translate an entire solution in the graph view to an entire solution of the integer program, and vice versa. And so realizing one trajectory, tau1 and M1, is equivalent to realizing tau2 and M2, even if the intermediate states are not directly translatable. So the question is, when does having two views help? And we studied two cases, and in the interest of time, I'll only show you one result, and that is in the policy improvement setting. We also looked at bounding optimality gap under stronger assumptions, and both of these build upon previous work, which we then extend to the co-training or policy learning / decision-making, sequential decision-making regime. And so here is a summary of our policy improvement bound. This is the main mathematical slide in this talk, so please bear with me as I walk through it a little bit in detail. So this is a somewhat standard-looking policy improvement bound that you would see when analyzing various policy gradient algorithms in reinforcement learning and also imitation learning. So J here, as you also saw in the previous talk, quantifies the overall performance of our policy. And so pi prime is a new policy that we're updating. So here, without loss of generality, I'm only presenting it from the perspective of view 1. The same policy improvement bound also applies from the perspective of view 2 without loss of generality. And this J can be either in reinforcement learning or in imitation learning performance. Right now, we're agnostic to that. The way policy gradient works is that we evaluate this new guarantee, new bound relative to an estimate of pi prime 1 as evaluated as sampled from trajectories, the distribution of trajectories generated by our reference policy, which is pi 1. This is standard gradient-based optimization. And so the name of the game is, can we tighten the bound terms on the right-hand side? And so the gamma is the standard discount factor in MDPs. Alphas is the difference in the change in the policy as you do policy gradient. And epsilon is a one-step suboptimality of pi 1, also known as the maximum advantage of the advantage function. And these things are all standard for any policy gradient analysis. So nothing has changed here. What's new are the remaining terms on the far right-hand side that we introduced in this analysis. And so the beta is a divergence measure or a difference measure between pi 1 and pi 2, between the two different views. Note that this is only on the set of problems where pi 2 is better. So we're looking at the improvements. The next epsilon is a suboptimality, so how much pi 2 can improve. And the last term, and we want to minimize this. So this bound gets better if these terms get smaller. And then the last term, delta, is the performance gap of pi 2 over pi 1 on the problem instances omega 2 where pi 2 is better. And that we want to maximize. So this is a valid bound no matter what. And the goal is to find a policy gradient algorithm that can minimize the first two and maximize the last one. And so this is just to summarize the intuition or the interpretation. And so here's our algorithm. It's called, it's a very unimaginative name. It's called COPIER, which stands for Code Training for Policy Learning. So first we sample an MDP from our distribution of MDPs. Then we roll out both policies. And then we do an exchange where we compare the quality of the two full trajectories, see which one's better. And then if pi 1 is better, we give pi 1 to pi 2. If pi 2 is better, we give pi 2 to pi 1. And then the other policy gets no feedback. We do an update rule, which is basically our normal performance bound, which is a performance measure, which is J, plus an imitation learning loss relative to the translated trajectories. And then we repeat. That's the entire algorithm. There are more details, of course, but that's the high-level idea. And now let me go on to some experiments. So I would just show one in the interest of time, and I'm going to walk through this slide a little bit carefully. And so this is on minimum vertex cover. This is actually a pretty challenging problem. We're going all the way up to about 500 vertices in a Eros-Renyi random graph. So this is a quite challenging optimization problem, even for commercial solvers. And so you have 4 sets of results from 100, 200 vertices all the way up to 400, 500 vertices. The first thing I want you to note is that we have strong baselines, strong performance versus baselines that don't use code training. So for example, the dark green line is our approach on the graph view, and the purple line is the standard RL approach on the graph view, and you notice that we're better. Next, we look at the orange line, the orange bar, which is our approach in the integer programming view. Compare that with the brown bar, which is the standard baseline approach using imitation learning on the integer programming view. So this is a direct view consistent comparison. Again, you notice that we're better. And so this is promising. It shows that indeed using both views simultaneously leads to much more efficient learning. Next, I want to note that if you combine the two views, so what that means is you run the policy on both views, and you compare the quality of the final solution, and you return the better one. That's the black line at the bottom. And notice that in this plot, everything's relative to the black line. So all of these numbers are in terms of relative performance gaps. then it does. Then if you do that, the black line does better than either view in isolation. And what that means is that no view dominates the other view. Even if on average the integer program view is better than the graph view, no single view dominates the other. And if you take the best of both worlds, you can do much, much better. And finally, I want to note that the gold bar is a commercial solver called Gurubi. And we have very, very strong performance against Gurubi as well, and commercial solvers such as Gurubi. And so this is a very promising result in that we can learn from two seemingly very disjoint views, share information across them in a mathematically principled way, and achieve strong performance results that in these cases can outperform commercial solvers on a very challenging combinatorial optimization problem. Okay, so just to summarize, this, to the best of my knowledge, is the first formal framework for studying code training in the sequential decision-making regime for policy learning, both for reinforcement learning and for imitation learning. We derived novel theoretical insights based on both policy improvement bounds and optimality gap bounds, which you can find in the paper. This led to principled algorithm design, the copier algorithm, and very strong experimental results against various baselines. And if you're interested, here are the references. These slides are also available on my website. So if you're interested in any of the details on these slides, you can find them on my website. That concludes my talk. Thank you for your attention.